We present contact detection between fibers, high order makes a difference. Let us start with an example. We comb a single fiber from root to tip in a physics simulation using two state-of-the-art models. In green, the low-order discrete elastic rod model, and in blue, the high-order superhelix model. Looking at the shape of the fiber, both models give consistently similar results during the entire simulation. However, measuring the force applied by the fiber onto the comb tells a different story. Indeed, although the two force profiles are similar, both also exhibit a large amount of noise. Part of this noise, especially with the discrete elastic rod model, is due to contact points being added and removed, which creates force impacts that manifest as large spikes in these two graphs. These contact losses are due to the combination of a velocity-based contact solver with the low-order fiber model and are not what we focus on in this paper. Even if we filter out this first source of noise, we can also see lower amplitude oscillations that seem to get larger as the curvature at the contact point increases. Our paper addresses these purely numerical artifacts. As we will see shortly, these non-physical oscillations are due to the contact detection algorithms that are used in both cases. To see this more clearly, we move on to a more controlled setup, the three-point bending test. A flexible rod with some amount of natural curvature is laid down onto two supports and then pushed downward at its center in a quasi-static manner. We then measure and plot the vertical force at the center of the rod as a function of the vertical indentation. For this scenario, a semi-analytical model can be derived. We compare it against the results measured from our two computer graphics simulators mentioned earlier. For collision detection, we discretize the curves into line segments, as is usually done with these fiber models. Although all simulated curves match the analytical curve quite well, spurious jumps in the force appear. Moreover, the amplitude of these jumps increases with the curvature at the contact point, and refining the collision detection by using more segments does not make these artifacts disappear. We'll now show that these jumps are due to the inability of segments to represent a smooth curve accurately. Let us look at what happens when we project a contact point P, here in orange, onto the center line of a fiber, here in thick black. The pink point is the closest point to P on the curve, and the blue point is the result we get by approximating the curve with segments, here in red. As we can see, using segments to approximate the curve gives a result that is inexact, as emphasized by the gap between the pink and the blue points. This gap may, however, be reduced by increasing the number of segments used to approximate the curve. Note what happens to the blue projected point when the orange point goes around the vertex of the discretization. The segment-based projection stays fixed at the vertex, while the real projection moves smoothly. These stutters cause the artifacts in the simulation that we have seen in the previous section. They are caused by the geometry of the segments, and this time, increasing the amount of segments only partly fixes the issue. Note that, even with the high number of segments that visually approximate the curve very well, blind spots remain. As soon as the objects that collide with the curve go through these blind spots, sudden jumps in the contact force will appear. Hence, we propose a new high-order collision detection algorithm for curves. Detecting a collision between two curves may be framed as an optimization problem of two variables. The aim is to find the minimum distance between the two curves, or, equivalently, the minimum of the function f here. Once this is known, checking for contact amounts to checking if the minimum distance is lower than a given threshold. If the two curves are line segments, f is smooth and convex, and a closed form expression of its global minimum is easily derived. moving the segments around changes the landscape of F, but the minimum may be found in all cases, even if it is on the boundary of the domain under consideration. However, if the two curves are more complex than line segments, F is no longer convex and local minima may appear. In this case, the global minimum of F may no longer have a simple closed-form expression, and numerical methods are needed. To find the minimal distance between a pair of curves, we have designed a branch and bound algorithm. We start with two curve segments and progressively subdivide them until either we can prove that they are far enough apart or they are short enough that the desired precision has been reached. For clarity, let us first look at the minimization of a function of one variable with our algorithm. The same ideas apply when we have two variables. We begin by considering the entire interval over which we are minimizing the function f. At all stages, the active interval will be displayed in green. We then take a sample in the middle of the interval and mark it as our lowest yet by updating S star and D star. Then, we subdivide the active interval in two parts and look at the leftmost half first. We compute an approximate lower bound of f over this interval, which we call L. Since L is lower than D star, we cannot know at this stage whether the global minimum may be in the active interval. Hence, we again take a sample in the middle of this interval, then update D star and S star, then subdivide it. Now, we look at the second half of the domain. Again, we compute L, see that it is lower than D star, then sample the middle of the interval, update S star and D star, and subdivide the interval before moving on. We now go back to the first quarter of the domain. Again, we compute a lower bound L over this interval. This time, L is greater than D star, which means that the global minimum cannot appear in this interval because we have already found a better sample elsewhere. Hence, we discard the interval and mark it in red. For the second quarter of the domain, computing L gives us a similar result. The global minimum cannot appear in the active interval, so we discard it and move on to the next interval. We then continue taking samples and examining intervals, subdividing them when we cannot eliminate them, until we are left with intervals that are shorter than our tolerance delta. This gives us a value for S star that is within delta of the actual global minimum, and the algorithm terminates. One question remains. How do we compute the value L for a given interval, or, in the 2D case, for a pair of intervals? Given a curve segment, we can use Taylor's inequality to enclose it in a capsule. With two curve segments, the distance between them must be higher than the distance between the capsules that enclose them. This information is exactly what we need to compute the lower bound L in our algorithm. See our paper for more details. We now use our high-order collision detection algorithm, coupled with the high-order superhelix model, to simulate more complex scenarios. Let's revisit our previous single-fiber combing example. With our new contact detection method, the force profile is much smoother. Finally, we show that our method can scale up to thousands of tightly contacting fibers. We simulate hair wisps composed of around 2,000 superhelices each, with various natural curliness. Straight on the left, wavy in the middle, curly on the right. Once each wisp has relaxed to its equilibrium configuration, a virtual comb passes through the wisp from root to tip, creating thousands of frictional contacts that our algorithm detects accurately. Note how the individual fibers rearrange themselves differently at the end of the sequence, especially in the curly wisp, as they would in reality. We also measure the force onto the comb in this setting, both when using segments for collision detection and with our algorithm, here on the wavy wisp. Although one could expect the force noise to average out to zero over the many fibers, we instead notice a large offset between the two curves. This shows that noise due to segment detection actually accumulates as the number of fibers increases, eventually leading to largely erroneous forces that integrate too much dissipation. In contrast, our algorithm, which is free from these artifacts, is expected to yield more physical results. Our method, of course, applies to any friction coefficient. As an illustration, in this example, we vary the friction coefficient to simulate a, say, clean wisp on the left and a, say, dirty wisp on the right. Varying the friction coefficient results in visible differences. Look how the two final configurations differ. The dirty wisp is split into several smaller wisps. Finally, we showed some promising results regarding tightly coiled hair. This simulation, made with 100 superhelices, requires a larger resolution for the superhelices, 32 elements instead of 12, and involves many contacts, especially self-contacts, which makes it particularly challenging. Look how the wisp is extended and how it reshapes after combing, depicting a typical helical perversion. In future work, we plan to better assess and leverage the potential of our method in terms of contact force retrieval in order to explore the complex physics of fiber entanglements. Thank you for your attention.